Okay, so am I audible?
Yes, sir, you are audible.
Okay. So in the last class, I was discussing about yield point phenomena. I'll continue with that. Is it mentioned in the website like in which session I have to teach which subjects?
Yes, sir, for today it was mentioned dislocations.
Dislocations. I could not find that, so I was like confused what I have chosen. So
Sir, you can continue with any topic, like all the topics are coming in the gate, so.
that's why I'm telling. So what is there in the next class? It is fatigue or creep, I think.
Sir, in the next class it is creep.
Creep. Okay. So in the next class we will discuss creep. So today I have taken 2-3 questions, and this yield point phenomena detail I will discuss this in detail. So as I was discussing, when we do a tensile test for a mild steel, we get this kind of curve. Okay, so this is the upper yield point. This is the lower yield point. So why this and this region? This is due to formation of Ludus bands. So I'll discuss what these things are properly. So first let's see the overall composition. So this is our local composition of solute atoms. In steel it is carbon or nitrogen. So this is our overall composition. Like for 0.4% carbon steel, weight percent carbon steel, it is 0.4. Okay, so this is called interaction energy.
Sir, what is X and Y?
That depends on the location of the atoms, like in dislocation, this comes from the dislocation theory only. The interaction, this also contains XY component, like at what position you are looking. The dislocations have stress fields. At specific X and Y direction, there are specific forces on dislocations. There are long equations like x square plus y square. I don't remember exactly. Long equations containing x and y, and also Poisson's ratio. So that explains the stress field of dislocations. From that, this xy comes from there only. Because at specific points, suppose we have a dislocation here, another dislocation suppose here. So these are specific coordinates, these are specific coordinates. So according to the coordinates at which point another dislocation is present or some solute atom is present, there will be forces according to that only. So in the equation of forces on dislocations, this x and y is incorporated. That's why they have given this x and y.
Okay, so means this is actually representing that out of the total number of carbon which is present within the matrix, how much is
Along the
present?
dislocations.
Okay, okay, okay,
Okay.
okay. Understood, understood.
Okay, so this interaction energy that depends on the location of dislocation. Like we have dislocation something like this. These straight lines are coming. There is a half plane. Okay, so at this position we have more room for solute atoms to segregate here. Like this is like a half plane, it is going through the plane of this screen. Okay, so here we can have dislocation like solute atoms, carbon atoms, they will get segregated along the dislocation line. Can you imagine the dislocation line? It is straight going towards into the plane of this sheet, plane of this screen. Okay, dislocation line, this is the dislocation, this is the half plane, and from this point I'm pointing here, from this point into this plane the dislocation line is there. Are you getting it?
Yes, sir.
Okay, so along the dislocation line we have the segregation of solute atoms, and that concentration depends upon the interaction energy, like is it compressive stress field or tensile, because below the dislocation line we know this is tensile stress field, remember this, and above this here we have compressive. Because here above this plane the planes are compressed, but here there is more room, so it is tensile stress field. So what is Cottrell atmosphere? So along the dislocation line we have, suppose these are carbon atoms, they go and sit there along the dislocation line. Like suppose I will draw this sideways, so this is the half plane, let's suppose. Okay, so here the carbon atom, because there is more space there and the stress field is tensile, so there will be attraction for these smaller atoms to go and sit there. So by these things what happens, they pin the dislocation. Okay, so what happens, by pinning the mobility of dislocation is reduced. So this is the reason we see an upper yield point. Like here I have shown this point, we have to go to certain higher stress to break the Cottrell atmosphere. So to remove the solute atoms from dislocation we have to go to a bit higher stress, that's why this upper yield point appears here. The reason for this is pinned dislocations, and second is low mobile dislocation density. And then we see there is yield drop. This from upper yield point to lower yield point, this is called the yield drop. Okay, why this happens? Because at some stress, this stress, suppose enough stress is reached so that we can break the quadrille atmosphere. So there is a burst of free dislocations, like the carbon atoms when they are removed from the dislocation core, these atoms, not just one, this is I am showing just one dislocation, there are many dislocations which get freed by removement of these atoms. So this is the strain rate at the upper yield point. We know the relation for strain rate due to dislocation movement, that is rho u b vu. This is the dislocation density at the upper yield point. This is the Burgers vector of dislocation, as is the velocity of dislocation at the upper yield point. Similarly, for the lower yield point, we have the strain rate rho l b vl. And we know in the tensile test we are applying a constant strain rate, so these all should be same. So the strain rate is equal to E u dot equal to E, this is L dot. So what do we get from this? Rho u by rho L remember this relation. So question will ask at the upper yield point the dislocation density is this and the velocity is this, and the lower yield point the dislocation density is this, so find the dislocation velocity at the lower yield point. You can directly use this. Any doubts here?
No, sir.
So further we can write, this is the velocity, this is a constant, this is also a constant. So now we can write in terms of shear stress, this is the applied shear stress tau. This comes from this relation only. V and tau are directly proportional. So if we get the power of 1 by m, then this m will be removed. So we get this relation. And we know Vu by Vl, that is rho L by rho u. This one also remember. Now what are Luder's bands? So suppose we have a tensile solution, this start forming after we reach lower yield point. So suppose we have a tensile specimen like this. So here you will see after you have reached the lower yield point, bands will start forming like this. So how this forms? These are the regions of high mobile dislocations. So what do we mean by that? Initially the dislocations are pinned by carbon atoms okay, initially these are pinned by carbon atoms or nitrogen atoms, whatever. There are so many dislocations that are pinned, so the density of mobile dislocation is low initially. So after it reach the upper yield point, this quadrille atmosphere that breaks, so the dislocations become free. Okay, so the density of mobile dislocation increases. So at certain this is the region at which there is much number of mobile dislocations. Are you getting my point?
Yes, sir. Means like if that after the upper yield point, since now the dislocations have been freed from the solute atmosphere, they will tend to form the Schluter band.
Dislocation actually yielding is basically movement of dislocations. That's how slip occurs, and slip is the reason for yielding of material. Okay, so at certain regions we have so many dislocations. So at this point this band forms, and what happens then? Uniform. After that, uniform elongation will take place.
Sir, so you said that these bands are forming. So, like, is there any particular orientation of these bands, or they are random bands formation?
They form certain angles like 45 degrees approximately, or something like that. They're not straight.
So, because like in when like in my coursework, I did this tensile test on mild steel, and we observed these bands. So we observed it to like we could not observe it properly, but whatever we could see optically, they formed randomly type of thing.
What was the angle like?
Sir, it was like about 55 degrees, sir.
55 degrees, yeah. I'm not very specific why that angle forms, but 45, when we apply stress, 45 degrees is the highest shear stress. At 45 degree we have highest shear stress.
Yes, sir, that's our principal plane lies on that angle. Yes.
That's
yes.
where the maximum shear stress plane lies, at 45 degrees. So those that could be the reason for this. I'm not sure.
Okay, sir, we will discuss.
Okay. So uniform elongation will take place inside the Schluter band. So suppose these are the grains and deformation is taking place, uniform deformation inside this region. So what happens? Dislocations will start moving and they will accumulate along the slip plane. Suppose it has slip plane like this. So dislocations will start accumulating here. This has like this, dislocation will start accumulating here in every grain. So then what will happen? In grains as per their slip lanes. So what this will cause? This causes stresses along the neighbor grains. So what happens when deformation is happening only in this region? That means the dislocation are moving and they accumulate at their slip planes. Okay, suppose we have a slip plane for one grain. The slip plane is like this. For FCC material, suppose this is 111 plane and this is the grain boundary. So dislocations will start moving in this direction. When they reach the grain boundary, they cannot move any further. So they will accumulate near the grain boundary in their slip planes. This will cause stress for this grain. Okay, so what this will cause? So the effect will be dislocation, unpinning. Because for unpinning we need higher stresses as per higher yield point, the upper yield point. Similar situation will happen here. Dislocation, unpinning in neighboring grains. Okay, so this can lead further to formation of a second Luder band. Okay, so this is how this forms. First one band will form, then another will form, then another will form, until uniform elongation takes place along whole the gauge section. And sometimes what we see dynamic strainaging. So what does this mean? When you do a stress strain curve, not for steel, suppose for any material, you go straight like this, then we'll see some kind of serrations all over to the fracture. So why do this form? This especially occurs when we do at very low strain rate. Or we do testing at high temperatures. So at low strain rate, what happens? Dislocation velocity is so small that the solute atoms that can move at the same speed at that of dislocations. Okay, so what happens here, once we break the solute atoms, then we have given very low strain rate. So what happens, as the dislocations moves, the solute atoms also move and they get pinned again. They get the dislocation pinned again, and again that breaks, again they go pin. So this process continues. That's why we get this serrated up and down, up and down, up and down behavior. And at high temperature, we know the diffusion rate is fast. So the solute atoms can easily move and get to the dislocation core and pin them. So at high temperature also we see the same behavior.
Sir, but at high temperature, the mobility of dislocations will also increase. So, like, will the carbon atoms able to catch them?
Carbon small atoms, they are interstitial atoms, so they will diffuse faster. If you take substitutional atoms, then they can't diffuse at a faster rate because they need vacancies. But for interstitial atoms, like we have atoms here. Suppose we want a substitution. This is interstitial atom, so it can move here, 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 any direction easily. And suppose we take a substitutional atom. Suppose this is the atom we want, substitutional atom that we want to diffuse. So we need at least a vacancy. Here I have given this vacant. At least one vacancy is needed to move. Suppose it have to move this direction, this position must be vacant from before. That's why the activation energy for substitutional diffusion is higher. Okay, for interstitial, there are all places are vacant, so it can move anywhere. It can diffuse much faster. C, N, H, these atoms.
Sir, can you once go to the previous slide, sir? Sir, like here they said that this dislocation unpinning in the neighbor grain, which will lead to the formation of a second Luder band. So, sir, like in the neighbor grain means, is it like that the carbon atom is also getting shifted, or the carbon atom from the next grain is like pinning it?
Carbon atoms, actually if you see, we don't need much carbon atoms to pin the dislocations. Okay, if you calculate, suppose we have a dislocation like lattice parameter, or the distance between atoms is given. If you calculate, we need really small, very small number of carbon atoms to pin a dislocation. So even you have like 0.4, 0.6 is too high. Actually, you can check in Raghavan book, I think material science, there is one question is there. How many dislocations, how many carbon atoms concentration is required to pin a dislocation? There I have seen like very small number of carbon atoms are required. So this will not affect the concentration much.
Okay, okay, sir. Okay, sir.
Is it visible? I should.
Sir, it's a Venturi meter question.
Yeah. But you will get this type of questions every year. And 2 marks.
Okay, sir.
So the question shows the schematic of bench emitter. The cross sectional area is 100 mm square. Okay, at A it is 100 and at B it is 50. Flow rate is given 10 to the minus 3 meter cube per second. And all the data are given. Impressible flow, density of air is 1 kg meter cube, density of water is given, acceleration due to gravity is given. So to find out the height h in the air over water manometer in mm. Sorry. Okay, so how do we solve these type of questions? First, you have to take 2 points. Suppose here we take this is at P1 and this point we take P2. And we'll take this height as x. Okay, so first we balance the pressure because the pressure at this point and pressure at this point will be same. So we have to balance them first. So this is we are going in this direction. So P1 plus what is the pressure due to a fluid when you go down, that is rho gh, rho of air g, and this is we are going from this here to here. So it is x, the height is x. Okay, from this side here to here, what will be the pressure is equal to P2 plus rho of air g. What is this distance here to here?
X minus h.
X minus h plus this one. So you can simplify this P1 minus P2 . This will get cancelled, this and this will get cancelled. Let's open it up. Okay, so you get this. This is the first part. Now what we do, we use Bernoulli's equation. That means this term is always constant at any point. Okay, so we have P1, rho air, V1, all these things are there. V1 square by 2g plus Z1. So because P1 and P2 are at same level, okay, these are the same level, so this Z1 and Z2 will get cancelled. Equal to B2 square minus B1 square by 2G. Okay, so P1 minus P2 you have calculated already. What is that? Rho WGH. We'll put that here. Okay, so to find a relation between V1 and V2, we know the flow rate Q equal to AV. So that means we know from continued A1 V1 equal to A2 V2. And area 1 is given 50 and other is given 100. 100 mm square at A and 50 mm square at B. So it implies that V2 equal to A1 by A2 V1. So this is basically 2. So V2 equal to 2 V1. Okay, so we put this here. 4 V1 square minus V1 square by 2G. Is it clear till now? So this G and G gets cancelled. So rho WH by rho AR, that is equal to 4 V1 square minus V1 square by 2G. So I'll write that here. Rho W is given 1000. H we have to calculate. density of air is 1. So 3v1 square is equal to 2.98, 2 into 9.8 into 1000 into h. So what is v1? Q is given 10 to the minus 3 meter cube per second. Q is basically AV. To the minus 3 divided by what is area? Area is 100 mm square. That means 100 10 to the minus 3. So what will be this? 10 to the minus 3 by 100, 10 to the minus 3 square. So with 10 meter per second. Q equal to AV. So Q is given this. We know the area 100 mm square, so we just divided by this and we get this velocity. And we put it here, V. In place of V1 we put 10. 3 into 10 square equal to 1000 into h into 2 into 9.8. From this we can calculate h. That will be so what will be this? Can anyone calculate this? 300. .0153 meter. This will be 15.3 mm. Okay, so this is the answer, 15 mm. So this is a huge question, like first you have to find this relation, then from this you have to put that in this Bernoulli's equation. Instead of P1 minus P2 you have to put V2 square minus P1 square. Then you have to use this continuity equation to get the value of V1. Then you find h. This is a question from 2020 I think, GATE 2020. So another question was there, like you have to calculate the number of atoms per unit area. Okay, so do you know how to calculate this? Number of atoms per unit area in 100 plane of lead. The atomic radius is given 0.175 mm and the structure is FCC.
Yes, sir, like we need to calculate the contribution of atoms in that area divided by the area of that plane.
Huh. Which is pretty easy. I think you first draw this plane 100 plane of FCC. How that looks like? We have one atom in the center, one in this corner, one in this corner, one in this, and one in this. And this is our atomic radius R, and this is our lattice parameter A. We know for FCC the relation is AA. This is root 2A. So root 2A equal to 4R. And what what is the number of total atoms here in this surface?
2, sir.
Because one completely is here, and this is 1 by 4, 1 by 4, 1 by 4, and 1 by 4. So just divide 2 by 0.494 square. Because the area is A square. This is our A. So I will get around 8 answer. This one you got completely, na? How I calculated this?
Yes, sir.
Okay, so one small thing I'll discuss. Do you know why austenite can contain more carbon than alpha iron? Like if we see the phase diagram, so this is the point where it is around 2%, and alpha iron, this is alpha region, this is gamma region, this is around 0.025 weight percent. So why such a huge difference? We know that carbon atom goes to the voids. Octahedral voids, because it is symmetrical. In FCC it is symmetrical, and in BCC the tetrahedral voids are, even if the size of tetrahedral void is bigger than octahedral voids in BCC, still carbon atom goes to the octahedral voids. Still the carbon atom goes to the octahedral voids. Why? Because this has low distortion, so that minimizes the strain energy. But still, why such huge difference, like 2% to 0.025? Do you know the position of octahedral void in FCC? Where it is?
Sir, it's in the body center.
Yeah, this position. We have one atom here, one here, one here, one here, one in this surface, one in this surface. So all those make the octahedron. Because here what happens, this distance here to here, it's same as this distance, so it is a symmetrical octahedral void. But in BCC, what is the position of octahedral void? So this position is the octahedral void of BCC. Okay, so we have in body center one atom, here one atom, so this makes the octahedron. So this is our octahedral void. So why it is unsymmetrical? Because this distance here to here, it is same as the lattice parameter A, but here to here, this is not A, this is root 2A. Okay, so this is distorted void. So because of this reason, carbon atoms don't like to get into this much as compared to FCC. So that's why austenite has far more carbon concentration than alpha iron. Got it? In both cases, FCC or BCC, the carbon atoms goes to the octahedral void, because tetrahedral void is far more like distorted, much more distorted. So it prefers to go to the octahedral voids. And in FCC, the octahedral void is perfectly symmetric. So more carbon atoms can be occupied in that. That's why we have around 2% in austenite and around 0.0258% in alpha, because of the distortion of the octahedral void.
Sir, so means if the carbon atom is suppose diffusing, so it will diffuse only through the octahedral voids, or like during diffusion it can occupy any of the voids?
During diffusion, it may occupy any of the voids, but it prefers to go to the octahedral voids.
Okay, sir.
During diffusion, I think it can go through any void. This is a good question actually. We know for sure that carbon atoms are occupied in the octahedral voids for this reason, for symmetry. But it can go to the tetrahedral voids, but that will make the structure more like high energy structure, so that will not be stable.
Sir, because we know that in case of cubic structures, like the number of tetrahedral voids are always greater than the number of octahedral voids. So if during diffusivity, if the carbon atom is also occupying tetrahedral voids, then it would be easier for it to travel.
That could be. Maybe some portion of carbon atoms are occupied in tetrahedral voids, but mostly they prefer to go to octahedral voids, because that doesn't cause much distortion. We'll see. I'll check that. I haven't seen like this type of things in any books. They have not mentioned anything. Maybe if you find something, you tell me.
Okay, sir.
Okay, so we'll end this today. See you next week.